Yeah, thank you very much. Welcome, everybody. We're excited to be here and to have the chance to talk about a work which we have done together with these two organizations, Capgemini and Airbus. So my name is Jasper Krauser. I'm the quantum coordinator, and I'm here with Adrian, who is from the quantum computing team at Capgemini. So together we explored how quantum computing could help us in modeling corrosion effects, and that's actually a very important problem for us. And why? Well, if you look at our portfolio, then this becomes a bit more obvious. So probably you know Airbus best for its commercial aircraft. Maybe some of you have even taken an Airbus to come to this conference. You see one of them here on this slide. So we have roughly 10,000 or more than 10,000 aircraft in operation. So about every 2-3 seconds, one of our aircraft is taking off somewhere in the world. So it's really our most important product. But Airbus is more than that. We are also producing defense products. You see, for example, military aircraft. We are the largest helicopter manufacturer in the world, and also Europe's largest satellite manufacturer. So what does this mean? This means basically one thing is common for all of our products. They are operated in difficult environments, from the very extreme in space to vehicles which operate in the stratosphere to commercial aircraft, for example, operating, let's say, at 30,000 feet. So this is why it plays really an important role for us, but it's also not the only case we are working on in Airbus thinking where we can apply quantum computing. So we have started, let's say, roughly 8 years ago to look into quantum computing. We have a variety of use cases, and we're clustering them along 4 different pillars. One is quantum optimization. This is quite similar to other end users. So we have a lot of combinatorial optimization problems, for example, in flight management or satellite operations. The second cluster, which is very important for us, is what we call quantum solvers. So this is more a macroscopic modeling meaning in terms of solving complex sets of equations. For example, to do aerodynamics or aeroacoustics. And this is a very important field for us, even though quantum computers are not yet, let's say, widely explored here for this topic. But this is actually where we have most of the need for computational power. Third cluster is quantum machine learning. So we are trying to limit ourselves here to very specific applications where we think there could be a kind of acceleration for our classical AI tools, and quantum simulation. And this is also where all, let's say, microscopic topics come in, microscopic simulations, and also the things which are interesting for us in terms of materials and material degradation, including corrosion. And I would like to use this opportunity to recap, because we had one activity this year where we joined our forces with BMW. We launched the Quantum Computing Challenge at the beginning of this year. So we formulated problem statements together with our friends from BMW, which are both relevant for the automotive and the aviation sector. And you can probably imagine that corrosion or everything which is linked to that is one of those common topics. So one of the use cases was what we call smart coating. And smart coating means, in this sense, it's how can you optimize materials, how can you include in the material matrix chemicals which stop corrosion processes or at least slow them down. So this was one of the challenges. We had a huge response here from the community. We're very, very happy about this, and just wanted to highlight the winner for this particular challenge is actually not very far from here. It's the University of Southern California. So this is about corrosion inhibition, but the corrosion process itself, right, is something which is important for us, not just for us. It's a concern actually for many sectors with a huge economic impact. For the aviation sector, it's mostly threefold. It's impacting our operational efficiency. It's impacting our the lifespan of our products, and also the maintenance cost. So there was a huge progress over the last, I would say, decades, that corrosion is now handled from an engineering level in a much better way regarding new materials. So we are using today, for example, titanium in the aircraft. We are using carbon fiber materials or composite materials, which are much less exposed to corrosion. And there's also a significant improvement in the protective layers and sealants, which are put on the materials to protect them. Nevertheless, we are relying still on aluminum alloys, and this is also likely to be the case in the future. And aluminum is, for example, in particular, also those which are relevant for aviation. They are impacted by corrosion. So if you want to zoom in what corrosion actually means, what's happening, basically you have a damage in your protective layer. So the surface of your aluminum is exposed to the environment, to oxygen, to electrolytes. And if you zoom in on a mesoscopic scale, so here you see a 5-micron zoom in, then you see that there's a chemical reaction setting in. This reaction is basically, it actually has some similarities to what's happening in batteries. So it's setting off a reaction which basically deteriorates the surface and the structure of the aluminum alloy and then has an impact on the macroscopic properties. So in order to handle this, you probably understand it's a highly multi-scale problem. So we are starting from a macroscopic effect. There's a lot of modeling done today on an engineering level using FEM methods, and these methods are very good. So they are able to capture a lot of the physics. However, you need to include microscopic parameters into those models. You can measure those microscopic parameters, for example, in the lab. So this has, of course, advantages because it's cost. It takes time. And also, there's one big issue. You do not have access to all microscopic parameters via the measurements. So this is indeed a limitation. So this is why there's a lot of quantum chemistry efforts using classical computation going on today. It's also quite successful. However, there are elements in the corrosion process where strong correlations play in. So the classical methods have uncertainties. It's also very difficult to predict the accuracy of those methods for all cases. So how do we treat now those corrosion reactions with the quantum computer? So we focused on one particular reaction, which is quite important in this context. It's the so-called oxygen reduction reaction. And how we do this, it's basically shown here in the slide. So we start from an absorption state. So the O2 molecule is absorbed at the surface. Then it goes into a transition state, so the molecule is broken apart. This has a higher energy, and then it's falling back into a product state when it's on the material. There's a second process. You see like a second step there, which is a diffusion process, which is less exposed or not exposed probably to strong correlation. So this is just a second. It's not so much of importance when we do the modeling here. So what does this mean now? What we want to understand and what is important is this what is called kinetic, so the activation energies. The larger this barrier, the slower is the reaction, or the other way around, the slower the barrier, the faster the reaction occurs. And this is the information we need, and this is also what the engineers practically need when they think about designing new materials. And how we model this, I would like to hand over to Adrian.
Thank you, Jasper. As Jasper has said, one of the most important pieces of information that you can get from a reaction mechanism study is the nature and the magnitude of the barrier. As anybody can tell you that has worked from the computational point of view in chemical kinetics, getting accurate kinetic barriers is far from easy, in particular because the correlation energy is very large, and you have to recover a very large amount of that correlation energy in order to get even chemical accuracy. I think I did. Yeah. So in this next slide, what I'm showing is two profiles of the previous mechanism that we have computed. It's the same profile computed with two different methodologies. In first place, we have Hartree-Fock in green. That is a methodology that doesn't include any correlation. Then we have a density functional theory methodology, in particular the PBE, that includes mostly dynamical correlation. As you can see, from a quantitative point of view, both profiles are quite different. But you can infer they both hint towards the first step as the rate limiting step of the reaction. So the one that is going to control the kinetics of the whole process is the first step. That is associated with the dissociation of the dioxygen molecule. We also compute the same profile using full CI methodologies, but using a very limited active space. We have considered 3 different active spaces of increasing size. And as you can see here, what we see is an increase in the barriers. And one thing that is very important, you see on the top, we are plotting the correlation energy. These methods, full CI with a small active space, they are better at incorporating static correlation than dynamic correlation. And what we see here is around the transition state, there are big changes on the correlation, on that static correlation. So we know now that this is a problem where the static correlation is going to be very important. And we believe then it's a problem, it's the kind of problem that quantum computing is going to show an advantage in the near future. Those are the density of states, the DFT density of states of the different structures involved in the mechanism. As you can see from the first 3, we see that the first step is indeed where the oxidation really happens. So if you analyze those density of states, you will see that some electrons from the copper are jumping into the anti-bonding orbitals of the oxygen molecule. That is going to weaken the bond, and it's going to facilitate the breakage, and finally you will end up with an S structure that we call the cis. The next step is less relevant. Once again, we know that there is a lot of static correlation involved in that first step, and we believe it's precisely because of that. There is a change there on the character, on the chemical character of those oxygen atoms, and we believe it's what's triggering that need to have more than one configuration in order to represent that transition state. This concludes the presentation of the first part of the study, that is a mechanistic study. And we are going to move to a second part where we did some resource estimation of what we will need from a quantum computer in order to run this type of calculations there. And we consider 2 algorithms. We consider BQE and we consider QPE. So we estimated, for example, the depth of the circuits, the number of 2-qubit gates that we will need. But I think the most relevant part of the BQE is seeing that in an ideal situation when we don't need quantum error correction, BQE will be very competitive with classic calculation. It will be faster. It wouldn't take much time even for those small systems, and it will be already competitive, and it will be faster than a classic computer. The problem is we need quantum error correction. And then the overhead that you introduce makes those calculations not competitive anymore with classic computations. So this is painting kind of like a gloomy picture of the situation with BQE because, of course, if we have very large systems, at this point, we cannot run them in current hardware. So you cannot go that route. And also, we are seeing here, if we have very small systems, we can run them, but they are going to be slower than what you can get using regular HPC. We also consider the QPE algorithm. We consider in this case only 2 active spaces. And what we see here first, as expected, is QPE compared to BQE requires several orders of magnitude more gates, deeper circuits than BQE. Nothing unexpected there. It was kind of surprised. We were kind of surprised to see that if you don't need error correction, well, again, this algorithm could be very competitive, and it will be also very competitive with BQE. But the reality is we need error correction at this point. And of course, if you consider the overhead of the error correction and also the sheer size of the systems, you will need to run these calculations, BQE calculations, even for those QPE calculations, even for this small active space. You know that this is not something that is going to happen now or in the near future. So I want to just read the conclusions of this study. From the mechanistic study, we have linked the macroscopic and atomistic corrosion modeling, a stepping stone to bring value in business use cases. For the first time, we have demonstrated the usage of quantum computing applied to problems in the field of corrosion. And also, we have seen from our mechanistic studies that corrosion mechanism, the oxidation mechanism associated to this corrosion process, It's going to have at least a rate-limiting step. It's going to have a strong multi-reference character. Our resource estimation reveals that significant advancements in QC algorithms, in quantum computing algorithms, and also in quantum error corrections are needed to make them valuable. I just also want to thank you, everybody, for attending this presentation. And I want to tell everybody that if anybody has questions also about this paper and they want to deep more into this project, we have recently published a preprint precisely of this project that is available online, and this Q code should redirect you to such paper. So thank you, everybody.
Thank you, Jasper and Adrian. If you have any questions, please use the QR code to transmit them to us. Right now, we don't have questions, but maybe we can wait a little bit, see if any come in. Maybe in the meantime, I have a question, if that's OK. So yeah, we saw that we need like a lot of quantum resources for some of these algorithms. Do you have like some directions in which you are working to reduce these resources that you would be comfortable sharing?
Yeah, I'm not personally working on that, but I know some people are considering, OK, not BQE, maybe move to different algorithms, for example. And probably, and that's outside also the scope, I'm more of a computational chemist that try to apply tools to computational chemistry. I'm sure they are probably checking into more efficient ways. This is quantum error correction, but I believe it's the most standard way you can do quantum error correction, so it's not a state of the art. I'm sure they are checking into it in order to get there to see how much it can reduce, and maybe with a different algorithm that is not BQE, maybe there are chances that, not tomorrow, but maybe in 5 years, with the new computers coming, that those calculations can run in the new computers.
Nice, thank you. So we have one question that came in. The question is, does the VQE runtime include the iterative optimization?
I believe so. I believe what they did is they ran one optimization, one shot. They got the number of gates. They multiply it by the number of the time that each gate, in average, takes to run. And then they multiply by the number of shots that I think is around 1,000. Everything is in the paper. So if you want to, I don't want to mislead anybody, but I believe those are the numbers. And that number, the runtime, yeah, include that. And that's the reason it's competitive with QPE when you are not included quantum error correction. Because QPE, OK, you have to maybe run many shots, but you run all your system once. No, yeah, I believe that's the.
Thank you. And we have a question maybe for Airbus. What are the other areas Airbus is exploring for quantum?
Yeah, I was showing at the beginning this overview, like say, I mean, we have these 4 different areas. I mean, since quantum simulation is something, let's say, very interesting and also maybe requires a bit less resources, hopefully, than other areas. There we are also looking, for example, there's recent work we have been doing also with BMW on fuel cell modeling. So there are quite some interesting problems for us which could help in the future our engineers to, let's say, design better products. There's a kind of design guideline. This is at least the hope. We have also optimization problems. Of course, we see all the issues at the moment with the scalability. For us, we are focusing quite a lot on what I was mentioning, quantum solvers. So it's still very a new field, I would say. It's not extremely developed, but it's very, very interesting for us because if you look like how many jobs today are performed on our classical HPCs, and we have quite a powerful system as an aerospace company, then it's by far the most are aerodynamics and then aeroacoustics. So this is really driving our industry, and this is what if at some point a quantum computer can accelerate elements in those calculations, this would be very important for us.
Great. Please join me in thanking Jasper and Adrian again. Thank you very much.
Thank you.